begin with a big shout out to the organizers of TRIPS-2025 for putting up such a wonderful show. I thank them for inviting me, especially to celebrate the stupendous achievements of my friend Astosh. It's been a privilege indeed. So, since it's going towards the fag end of this workshop, I will talk about the last letter in TRIPS, which is sustainability. And specifically, I'm going to talk about the development of sustainable chemical process through a process called electrification, and how process design techniques can be used to come up not only with a sustainable process design, but also an economically viable process design. That's what we're going to talk about. Acknowledgements to my student, PhD student recently graduated, Chaitanya, and a collaborator who's academic. So, how do we actually develop a sustainable chemical process? One of the, just to give a background, the process industries consume about a quarter of the total energy, and that includes refined waste, petrochemicals, fertilizers, and other bulk chemicals. So, out of this total energy consumption, about 80% of this is thermal, and about 20% is electrical, which is used to drive the pumps and compressors and so on. So, electrification, one of the paths to sustainability is to electrify the chemical process, which is basically substitute quite a bit of the thermal energy with electrical energy, with the hope that most of this electrical energy, which will be either drawn from the grid or locally generated, will be from renewable sources. Not just solar, wind, but also nuclear. Small modular reactors, people talked about it, could be used. So, as long as the electricity is coming from renewable, you have basically made your process sustainable. And there are several approaches to this. I think Prof. alluded to use of electrochemical process. That's a big drive. How do we actually produce chemicals through the electrochemical route rather than the thermal route that we are currently using? And also there are other possibilities such as use of electrically heated boilers. For example, instead of using fuel, fossil fuel, why not electrically generate the steam that we require for direct heating or for generating power in the plant? And also there are other possibilities such as using heat pumps in distillation or waste heat recovery and so on. So my talk is mostly going to be concerned with the use of heat pumps and in what you call in distillation as well as subambient process, and especially how do you design these processes where there is an interaction between electrical work and thermal energy so that it's also economically viable. Just to give you an idea, the cost of electrical energy is about 3 to 5 times as much as thermal energy. So unless for every unit of electrical energy you input into the process, you better gain 5 times the thermal energy. Otherwise, it's not going to be economically viable and industries may not even absorb it. So that's the key to keep in mind as a thumb rule when you design this. So, so there are several process design strategies. When I look at process design, it's a systems design. So one is the reductionist approach where you propose a whole superstructure of possible designs and then try to abstract the most optimal one through our optimization technique. Unfortunately, coming up with a superstructure requires imagination, and not always you'll be able to come up. There's some special cases you'll be able to come up with a good superstructure design. The other possible is an additive approach where you put layers upon layers and come up with the entire design. So this is called the onion model of process design. So you start with the reaction system, layer the separation systems on top of it, and then layer the heat and work energy system, and finally the control layer. So this way of building and then treating the interacting variables through an optimization technique can help you generate the best process design. And this is the approach that we have taken in order to look at how, at least 2 case studies I'm going to show. One is vapor recompression columns, how you can come up with a design that achieves the optimum trade-off between work and thermal energy, and the other is the subambient process, which is liquefaction of natural gas. So we can go ahead. So I'm not going to talk about the entire methodological development. I'm just going to apply it and give you the final results to show how effective it is. There are several different separations where the VRC has been proposed. VRC is basically, if you look at a conventional distillation column, you have use of what you call cooling utility at the condenser and use of heating utility at the reboiler. That's a conventional column. What you're trying to do is you're trying to integrate the two. But unfortunately, thermodynamically, you can't do it because the condenser is at a lower temperature compared to the reboiler. So one possible way is to take the vapor out of the column, compress it so that you increase the quality of the heat. So temperature increases. If you sufficiently compress it, then the temperature increases, so you can now transfer energy from the vapor stream to the liquid stream. And that way you can heat integrate the condenser and the reboiler. And that's exactly what's shown in the second thing, where you compress the vapor, then you exchange with the reboiler, and if there's any additional heat to be removed, you can use a cooling unit, or you can even preheat the feed. So there are different ways of doing this, and it's usually applicable for close boiling mixtures where the temperature difference between the top and the bottom product is roughly about 20 degrees or a little higher than that. But it's too high, then this is not a very viable option. If you go to the literature and find out what are the various configurations people have proposed, you'll find a variety of them, 20 different possible configurations. And in some cases, the energy from the after compression is used to both the reboiler and the feed. In some cases, part of the vapor is actually compressed, the rest is not compressed. You can preheat the vapor before sending it to the compressor, and so on and so forth. So you can come up with a variety of drawings, and if you are an excellent artist like Asutosh, he can come up with very fancy drawings also, I suppose. So each of these can be optimized, and you can try to find out which is better, but this is a very trial and error kind of approach. Is there a synthetic way of coming up with the design? And it turns out that one of the technologies that were very popular in the 1980s that came up with the thing and is very widely used in industry is the pinch technology, which came up with the idea of how to generate an optimal structure for just purely thermal energy exchange within the process. And it's very successfully deployed. There are software packages now that you can actually readily use for the design. But when you look at the interaction between thermal and work, you don't see such a very standard synthetic procedure available. And that's what we have developed. So the idea is to come up with this design structure automatically, right? So I finally only give the result. So this is the structure that we came up with propylene-propylene system separation, where you see the vapor being compressed fully, and a part of it is used to transfer energy to the reboiler, followed by some of it to the feed, and then it's again passing to the feed with the intermediate thing and so on. So this complex structure, or that's something falls out of the design procedure. And if you look at the advantage of this design, you see that it actually consumes 33% lower operating cost than any of the previous designs that have been proposed. All the configurations we can come up with, but this synthetic procedure that comes up with the design consumes only about at least 30% lower operating cost. And if you look at the power consumed, you have injected about 200 kilowatts of electrical power in the system, but you have saved about 3,700 kilowatts of thermal energy, which is clearly, therefore, economically optimal, right? In terms of using vapor compression. So we have tried this with very many different separation systems, and we found out that this procedure is able to come up with excellent cost optimal designs. And a second example that I want to talk about is the liquefaction of natural gas. Natural gas is being now considered as a good transition thing before we completely become carbon free. And if you want to liquefy, you can use refrigerants like nitrogen in this case, and you compress it and then expand it and cool the whole thing in order to get the natural gas which is indicated in red. The nitrogen itself operates in a closed loop. Right, and again, you need to consider nonlinear variation of specific heat with respect to temperature in the design, and finally come up with apply our procedure. Again, there are several different design structures that are proposed. Again, it's a trial and error, but if you apply a synthetic procedure, you can come up with a design strategy that gives you lesser power per unit of energy, liquefied. So this is again, in this case, 10% lower, but you can also get other kind of things which gives you 22% lower. So the idea is that you can come up with a design structure using the systematic procedure in order to get an economically optimal or viable solution which the industry can So I'm just going to stop here because the time's up, and these can be extended to any subambient design, what we call separation, air separation, air or helium production, and so on and so forth. And comes up with the PFD as well as the optimal process conditions. Thank you.